So I've got the formula, or the definition of curvature, up here on the board. Now, let's suppose I just have a very simple function, r of t equals t squared. That's just my basic parabola. And it would be oriented so that the direction of increasing t is moving to the right, because x is the same as t in this particular case. That is a smooth curve. So its curvature is defined. If this is the only formula that I have, then in order to find the curvature, I need to first of all find the arc length parametrization. Then I need to take its second derivative, and then I need to take the magnitude of that. And that's not sounding like a really fun problem, because we've seen that when you find an arc length parametrization, very often the formula gets messy. So conceptually, the notion of an arc length parametrization is very elegant. It's almost never elegant to actually work with it. So it's one of those things where it's great to know that it exists, it helps us in defining things, but it's very cumbersome to work with. It turns out that there are some equivalent formulas for curvature that allow us to stick with an arbitrary parameter t. Okay, so it's still curvature, but I'm just going to give you a formula in terms of t so that we can bypass that step of having to try to find trying to find the arc length parametrization. Okay, so one of these formulas is that it's a quotient of magnitudes. It's t prime of t, the magnitude of t prime of t, divided by the magnitude of r prime of t. Okay. And that's going to be a little bit easier to calculate, although it's still not ideal, because anytime I have to take the derivative of a normalized vector, that becomes a little bit tedious. Let's just take a quick look. R prime of t here would be 1, 2t. So the magnitude of r prime of t is going to be, the square root of 1 plus 4t squared. So that means that t of t, the unit tangent vector, is 1 over root 1 plus 4t squared, comma 2t over root 1 plus 4t squared. Oh my. Okay, so it's not too bad, but if I have to take the derivative of that, I'm going to be using some chain rules and some quotient rules and stuff like that, and then I've got to calculate the magnitude. It's starting to get a little bit tedious. Certainly doable, but it would be nice if there was an easier formula. Well, there is another definition of curvature, or another formula for curvature, but it works in 3-space. In 3-space, we can define the curvature to be r prime of t crossed with r double prime of t divided by, oh dear, I've got to refer to my notes, divided by the magnitude of r prime of t cubed. Quick note on the formula. You just caught me looking at my notes. I don't have that formula memorized. I just memorized that about 30 seconds ago. Okay. I know this. Okay. Here's my standard for this section. This is really the definition. And we were able to look at this formula, and we were able to see why that made some sense. This helps me to understand what curvature is measuring. But it's a royal pain to use it to actually calculate curvature for anything that isn't as simple as a line or a circle. This is derived in the textbook, and it's not a super difficult derivation, so it's okay. This one is a little bit more difficult to derive, but neither of them really I can look at and say, ah, yes, I understand what curvature is because of that formula. So these are the formulas that I think are easier to work with for actually calculating curvature. This is the formula that tells us what it means. Now, there's a handout posted on Canvas that tells you for this section which formulas you're responsible for knowing and which formulas I would give you if you need them on an exam. This you need to know. These I would give you if you need them on an exam. Okay, so as you're doing the homework, I would encourage you to use the formulas for curvature in terms of the parameter t because they're much more user-friendly. In particular, this one when possible. Okay, but if I ask you what is the definition of curvature, and I might very well specify, give it to me in terms of arc length, I would want you to know this. Okay, curvature is something that we're dealing with just in this section, so I don't see a whole lot of benefit to memorizing these formulas, but I do see a lot of benefit to your knowing that they exist and being able to use them. Okay, now this one is definitely more user-friendly than this one, because as I said, once you've normalized something and then you have to take the derivative, you're taking the derivative of a fraction where you've got square roots in the denominator, and while that's not the end of the world, it is a little bit tedious. Here, just taking two derivatives, taking a magnitude, oh, I'm sorry. That should have been a magnitude on the top. Curvature is a number, not a vector. I do apologize. I totally left off that magnitude when I wrote this down. Huh. Okay, I'm going to wake up. All right. So, this is much nicer because all I'm doing is taking the first and second derivative. Cross product is pretty simple. Two magnitudes, and then just put them together into a fraction. This is the most user-friendly one. The problem is, cross product is only defined in 3 space. Okay, so I'm going to show you a neat trick. And I'm going to caution you that you have to notate it correctly if you're going to use this trick. That means don't follow the book. The book sets a bad example in doing this. Okay, what I'm going to do, let me just write that formula up here. Oops. Kappa of t is the magnitude of r prime of t crossed with r double prime of t over the magnitude of r prime of t cubed. Okay, and notice we're cubing the magnitude. We're of course not cubing r prime because you can't cube a vector. Interesting to ponder. Okay, here's what I'm going to do. This curve is in 2 space. X's, y's. There are no z values. Okay, so it's in 2 space, which is the xy plane. Okay. Now, I can do what's called an embedding. This curved arrow here means that we're embedding in 3 space. I can create a new function. Its name is not r. That name is taken for this curve in 2 space. I am creating a new function. I can name it whatever I want if the name isn't taken. So I can't call it r, can't call it r prime, I can't call it t. I can call it r tilde. That's what I'm going to do. I kind of like that. I just put a little decoration on top of the r so I can see it has a relationship to r, but it's not the same function. All I'm going to do is I'm going to say rather than drawing this in the xy plane, I'm going to draw it on the xy plane in 3 space. So I will get t squared 0. That's going to give me this same curve, but in 3 space. So on the xy plane in 3 space. Is it the same curve? No. This is a curve consisting of points identified as vectors in 2 space. This is something consisting of points identified as vectors in 3 space. They are not the same, but they have a lot in common. Is the curvature of this going to be the same as the curvature of this? Yes. Okay, because all I'm doing is drawing that picture in a different place. But the identity of these functions is very, very different. I could add this to another vector function in 2 space. I could not add this to another vector function in 3 space. I could add this to another vector function in 3 space, but I couldn't add it to a vector function in 2 space. So they're not the same. And the book sort of glosses over that, and so they'll just start working with this without saying, hey, let's embed in 3 space and let's give it a new name. They're treating it almost as if that's the same as R. I understand why they're doing it, but I've seen enough students who actually treat this curve as if it's the same as this curve and try to add it to something in free space, which you can't do, okay? That I'm going to be very, very strict about that, okay? Now, if I want to calculate the curvature of this curve, it's going to be the same as the curvature of this curve. And so embedding gives me a new function, but a lot of the properties of the function will be preserved. Use your common sense about whether the properties that you're in question are preserved or not. Yes, the curvature is going to be preserved. So now I can use this formula to find the curvature. Okay. So what I want to do is find a general formula for the curvature, and I'm kind of interested in just finding the curvature of that point right there. Let's find the curvature at the vertex. Okay. So I need to find r tilde prime of t. Don't call it r prime, that would be in 2 space. R tilde prime will be 1, 2t, 0. R tilde double prime will then be 0, 2, 0. So now I can calculate the cross product. R tilde prime crossed with r tilde double prime is going to be the symbolic determinant I, j, k. R tilde prime was 1, 2, t, 0. R tilde double prime was 0, 2, 0. Now if I calculate that, I'm going to get some i's, some j's, and some k's. The i's and j's should both be 0. I know that because both of these vectors are in the xy plane. So their cross product has to be mutually orthogonal to these 2 vectors. They're not parallel to each other. Anything that's mutually orthogonal to 2 non-zero vectors that are not parallel to each other in the xy plane has to point in the direction of the z-axis, either straight up or straight down. Now I can confirm this algebraically. The number of i's is 0 minus 0. That is, in fact, 0. The number of j's is 0 minus 0. That is, in fact, 0. All right, the number of k's is 2 minus 0. Okay, so we get 0, 0, 2. Let's see. And so now I can say kappa of t is going to be the magnitude of 0, 0, 2 over the magnitude of r prime of t. That was 1, 2t, 0, and that one gets cubed. Notice this is just 2. This is going to be the square root of 1 plus 4t squared, and that quantity gets cubed. So that's my formula for curvature. We said we wanted to find the curvature at the vertex. That would be the point where t is equal to 0. The curvature at that vertex would be 2 over 1 cubed. It would be 2. Okay, so what that tells us is that this lovely parabola at its vertex, now I can see the curvature changes. It's not constant the way it is for a circle. But at the vertex, this has the same curvature as a circle of radius 1/2. Because remember, for a circle, the radius of the circle and the curvature are related by a reciprocal relationship. The curvature of a circle is the reciprocal of the radius. And so I can say if that's the curvature, that matches the curvature of a circle of radius 1/2. Kind of interesting. And in a little bit, we're going to actually talk about something called the osculating circle, which is like the round version of a tangent line. Instead of being the line that best approximates a curve at a point, it's the circle that best approximates a curve at a point. And it's just a question of, now I know what the radius should be, because it's going to be the reciprocal of the curvature. Just need to figure out where to put the center. We've got a little bit more work to do before we're ready for that.